Hello, 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 hello. Ah, hi, hi, hi. Good afternoon. Be careful about the coffee. It is too strong. Though I had three of them from the morning. Welcome to our technical session 2. This is Shamim Reza from all the way from Bangladesh. I work for a company named Team Phoenix. We are heavily working on cybersecurity. We breathe security, we eat security, and we do everything on security. We are focused on capacity building. We host the biggest cybersecurity summit in South Asia every year in May. So for 2016, please book your calendar for May and plan to visit Dhaka. We are also working on helping business secure their infra, those who needed it. So today's second session is more focused on security. We have 4 speakers from different area. And I would like to welcome Mr. Yihao Chen from Tsinghua University, China, to talk about BGP hijacking risk. So can we give a big round of applause for Chihao?
Okay, thank you, Shamim, and hi, everyone. I am Yihao Chen from Tsinghua University, and it's a great pleasure to be here. This is my second time to the evening conference, and I'm so excited to share some of our recent work on what we call the stealthy BGP hijacking risk in the specific context of partially deployed ROV in today's internet. And I suppose most of you are already quite familiar with BGP, and I was giving the basics and jump right into it. And first, let's take a look at the real case of BGP hijacking. And here's the picture. In this case, AS 17894, which is here, misannounced /24 prefix, which is part of /16 that is originated by its legitimate owner, 3758. So technically, this is a subprefix hijack that makes 17894 the hijacker. But I want to emphasize here that I'm using the terms hijacker and hijacking in a neutral way, and it does not necessarily mean 17894 acted maliciously. And as I'll show later, we tend to believe this whole incident was more likely to be caused by denial misconfiguration rather than a deliberate attack, and that's what I want to clarify here. Now, back to this case. What makes this case interesting is how ROV comes into play. Note that 37100 here was applying ROV filtering. So the invalid /24 route originated by the hijacker would end up being dropped by 37100. And that was good because ROV did its job and everything looked fine from 37100's point of view. It only had this /16 valid route to the correct origin. But things did not end there. The traffic from 37100 would pass the next hop, AS3762. But AS3762 was a legacy AS who did not apply ROV filtering, and it would instead divert the traffic towards the hijacker, according to the /24 route. So, in other words, the hijack still worked. And even worse, the AS37100 and its customers, which there are quite a few, are not seeing the invalid route in their routing table. So unless notified or by performing some kind of data probing for some reason, they would not know there was this ongoing hijack just by seeing their routing table. So this is the phenomenon in this case. And here is some evidence from 37100's looking glass. And as we show here, when we show IPBGP for this /16 prefix, it returned to route both with the origin, the legitimate origin, 3758. But when we show IPBGP for this invalid /24, it gave nothing, which means the hijacker was effectively invisible from the victims in their routing table. But in reality, the traffic was still hijacked, as the trace route here clearly shown that it ended up in AS 17894. So to summarize a bit, the traffic was hijacked, but the misbehavior was invisible from the victim's routing table. And as I mentioned earlier, we tend to believe this incident was caused by a binary misconfiguration, and here's why. AS17894's parent organization is Inno Communication, which is a subsidiary of Globe Telecom. And the 3758 parent organization is SingNet, which is operated by Singtel. And interestingly, Singtel is the main shareholder of Globe Telecom. So in this sense, on these networks, whether it is the affected one or the misbehaving one, are owned, sharing the same interests inherently, and any services impacted would be likely to stay within their own scope. That's why we think this incident was benign. Anyway, we notified Globe Telecom and about this incident, and they told us they would investigate it. Sorry. Okay. Now I would like to summarize what is alarming to us in this case, which is the BGP hijacking, whether it is intentional or not, still succeeds despite the partial ROE deployment today in certain cases, and even becomes less spotted or stealthier due to this incomplete ROE deployment. That's the phenomenon in this case. So in general, is BGP hijacking becoming more elusive due to partial ROE deployment? And what is the general mechanism behind this phenomenon? To get a sense of that, let's first take a look at how well ROE is deployed today. As is shown here, in today's internet, ROA coverage looked pretty good, about 56% coverage for both IPv4 and IPv6 prefixes. But when it comes to ROE, things look very different. According to APNIC, Rovista, and Cloudflare's measurements, only hundreds to a few thousands of ASs are enforcing filtering of more than 80% of invalid routes. This is still quite a small number compared to the overall 77,000 plus autonomous systems in BGP today. And not even on tier 1 ASs are enforcing ROE. For example, the 6762 in our case is a tier 1 AS. And generally, ROE is in partial deployment, and it's probably going to stay that way for quite a while. And that's the takeaway here. So under this circumstance, the views of BGP routing tend to become much more inconsistent across different points in the network. And here is the example topology generalized from our case. And we see in this general setup, the hijacker is ASG, who tries to hijack a prefix of the target, ASE, and their announcement join at ASC. And because ASB and ASD both apply ROV filtering, it is clear to say ASD and E, they are protected, while ASC and F, they are not. And the subtle part is what happens to this left rectangle here. What happens to ASA and ASB? Are they protected or are they hijacked? And to explain this, let's take a look at ASA, for example. From ASA's perspective, the hijacker G does not even appear on the control plane because of the ROV filtering of ASB. And from its perspective, it would expect its traffic to be safely forwarded toward the correct origin along this correct path, which is the green line here. And from a global perspective, however, traffic from ASA would go through ASC, which is an intermediate AS on this correct path who accepts the invalid route for the hijacker and who diverts this traffic according to this invalid route. So here's the key part. If any intermediate AS on your path has a different view of origin than what you see, the traffic diversion could happen. And partial ROV deployment just makes such inconsistencies more common. So that's how it happens, and we call it stealthy BGP hijacking. I want to emphasize that I'm not to discourage ROV deployment. And actually, as I'll show later, I think this is more like it is not a flaw in ROV itself, but more like an unexpected side effect or byproduct of ROV in partial deployment specifically. And yet it is still alarming or concerning because stealthy hijacking can evade self-operated control plane detections and even make post-attack forensics much more complicated. So now that we know this mechanism, it is natural to think about measuring how often stealthy BGP hijacking happens in the real world, and that is what we did here. And remember that the key part lies in the inconsistencies in BGP, in the views of BGP routing. And so we compared the routing tables from different vantage points using the route view collectors to identify potential stealthy BGP hijacking incidents. And we also used RPKI, IRR, and WHOIS for the check of prefix origin legitimacy. And we also use KDAS AS relationship data sets and more to identify some nuanced behavior that might link to some kinds of route engineering practices. And here are the results. In the first 2 months of 2025, we captured 1,394 observations of potential stealthy BGP hijacking, which translate to 18 to 29 incidents per day, with up to 5 new cases discovered daily. And when we deduplicate these observations over time, we have 110 unique incidents. And of these incidents, 69% last within a week, which is relatively short-lived, while a certain portion, 13%, are long-lasting. They last over 30 days. And these long-lasting incidents are more likely to be caused by unattended misconfiguration. And we also found 67 cases are showing some kinds of route engineering practices, for example, route aggregation. And we attribute this incident to improper operational practices. And we find 91 incidents involve subprefix hijacking, which tend to have a more serious impact. And finally, 22 incidents are directly observed from vantage points, which are of the highest confidence because these are the first-hand observations. And overall, these incidents in total, they affect 31 countries and 156 prefixes across 73 origins, and they involve more than 4,000 routes observed by 50 different vantage points. We also look into the number of vantage points that observe each incident, and we found that most of the incidents are observed by 3 or fewer vantage points, and only 40 and more than 40% incidents are only seen by 1 vantage point. So this tells us that the visibility of these incidents is highly dependent on which vantage points are we looking from. And to confirm this conclusion further, we conducted the experiment here. We randomly removed a certain number of vantage points, and we see how the visibility drops. And the results here, when we remove 20 random vantage points, there's a average 22% drop in the observable incidents, and up to 55% drop in the worst case. So to summarize, the takeaway here is stealthy hijacking in the wild is mostly short-lived and usually targets subprefixes. And new cases emerge almost daily, and some persist long-term. And this long-term incidents are more likely to be caused by unattended misconfiguration. And the visibility of these incidents is sensitive to what vantage points we are selecting. And here is the website. Beyond this 2-month study, we continue to observe the incidents in the internet, and we publish a daily report on our website. And this is it has some fancy features such as searching and filtering, and you can check it out. We are also experimenting a GPT analysis feature. There's an interface, and I will leave the link in the end. You can check it. And apart from this empirical study, we also conducted an analytical risk assessment, trying to figure out the general success probability of stealthy BGP hijacking in the internet. And due to time limitation, I will just pick out the most important finding. And long story short, we conducted large-scale BGP simulations on the empirical internet topology in 2023 and 2025. And we found that during this time, the ROE deployment increased a lot. And accordingly, the success probability of a random stealthy BGP hijacking also increased along with this ROE deployment increase. And this is quite unsatisfying. And the good news here is from the 2025 results forward, we continue to increase the ROE adoption rate and check the general success probability, and find out that from now on, if we continue increasing the ROE deployment, the risk actually goes down. So overall, it shows a rise than fall pattern here. And the good news is we are actually probably entering the declining phase now. So keep pushing the ROE deployment is good. And finally, I will leave some time for the discussions. And the limitation of this approach is more about the BGP simulation. And I would like to emphasize some of the operational insights. The first is for a network operator, stay alert about the discarded routes because they can include some information about potential stealthy hijacking. And also route collector platforms such as route views and the probing facilities such as Right Atlas, they actually help because the more coverage we have, the more coverage of vantage points we have, we can find more stealthy BGP hijacking incidents. And also, I think it is the time to start some document work. For example, the IETF internet draft. And also we should have some discussion about this issue to have the awareness of this. And there are also some countermeasures to this risk. For example, I'll pick the most important one. We can keep increasing the RPK and ROV deployment because according to our finding, once we increase this deployment beyond a threshold, the risk would go down and finally become negligible. And there are also some other strategies here. For example, the last one, we can have some smart strategies when we drop in invalid routes. We do not just simply drop this route, but also we start a reselection of the best route to ensure that the selected route does not include any ASs from this path in the invalid route. So there will not be any AS that can diverge your traffic silently. And that should wraps up my talk. And I hope there's still some time for questions. Thank you.
Any questions from anyone? Please introduce yourself and yes, sir.
Jeff Houston, I'll sit down because it's easier for me. The problem that you're explaining here, you kind of suggest that it's a problem in forwarding information when the origination was invalid. In actual fact, the real problem inside all of this is not that. It's the fact that nobody can validate the ASs that are in sequence in the AS path. And without AS path validation, anybody can attack the routing system. Because all you have to do is reproduce the originating AS and synthesize an AS path, and no one can tell that it's synthetic. So it's not some kind of hidden problem here. It's very simple. Without AS path protection, this system is about as good as an armor suit made of wet lettuce leaves. It just isn't resilient to determined attack because you can always attack on the path. So we need path protection. I'm not saying ASPA. ASPA has got topology and policy hopelessly confused. You actually need topology protection sitting inside the AS path, and that's the challenging bit. Thanks.
Thank you, sir. I think we don't have any time for any questions. So yes, thank you, Chen. Can we have a big round of applause for him?
Thank you.
So our next speaker is going to talk about cryptography in quantum era. He is none other than Mr. Paresh Khatri, our big fan and friend from Nokia. He is serving Nokia as the CTO and Chief Architect for IP Network Division in APAC region. So can we have a big round of applause for Paresh Khatri?
Thanks for that intro, Shami. Good afternoon, guys. Pleasure to be here in Da Nang. It's quickly becoming my favorite city in Vietnam, my second trip in a few months. So the topic for today is something that I'm quite interested in personally, and been doing a fair bit of work on over the last 18 months or so, which is looking at classical cryptography and the impact that evolution of quantum technologies can potentially have on that. So very quickly, the agenda, a very brief look at quantum computing some of the evolution that's happening there, some of the key concepts and technologies that play a part as far as cryptography goes. Then I'll go into the impact of that on cryptography that we use today on the public internet and really pretty much everywhere. And I'll wrap up with a look at the post-quantum future as we see it right now. Obviously, it may change, but we've got some idea of how we're approaching it. So I'll take you through that. Okay, so quantum technology. Now, when it comes to quantum technologies, you could say that there are two distinct eras of quantum technology. The first, which you call quantum technology 1.0, is something that we've been or whose properties we've been exploiting for some time now, right? So things like lasers, transistors, solar panels, and so on, they all use properties of quantum technologies. And in particular, the properties that we use are related to those associated with what we call an ensemble of protocol of particles, I should say. So groups of particles and quantum behaviors that apply to them. Now, we're actually extending that in terms of the applications. So with the current generation of quantum technologies, which we're calling quantum technologies 2.0, we're actually looking at the behaviors of individual quantum systems, right? Individual photons and electrons and so on. And some of the properties of them, such as superposition and entanglement and so on, and using that in order to come up with applications such as quantum computing. So this is a really fascinating area. It's an area of active interest, and it has a lot of applicability to us in the world of communications. So a few quantum concepts before I go further. Firstly, the idea of a qubit, right? So qubit is short for quantum bit. And in the quantum world, it is the unit of information, just like we have a logical bit that stores information about a digital quantity. It's either 0 or 1. We have something similar in the quantum world. It's called qubit. Now, what really differentiates qubits from today's logical bits is that unlike logical bits that can either be 0 or 1 at a single point in time, the qubit can actually exist in a superposition of states. It can be 0 and it can be 1 at the same time. Now, it's a pretty it's not easy to understand this concept, right? But think of this as a model that's being used to explain the behaviors that we see in the quantum world as things get really, really small. So coming back to this, right? The qubit is in a state of superposition. It's both 0 and 1 at the same time. And it doesn't take on any of these or either of these values until such time as it is actually observed or measured. When it's measured, that wave function that is associated with the qubit actually collapses and then becomes either 0 or 1, right? But until then, it's in both states. The third element of this is what we call entanglement. So this is where you could have a pair of particles or pair of qubits that are related in such a way that they share the same state or they share state. So for example, if you have a entangled pair of qubits in a state of superposition and you measured one of them, resulting in the collapse of its wave function, the same thing would happen to the paired qubit as well, which is a property that we use in some applications of quantum cryptography. So why talk about this? We talk about this because we can actually use this to build quantum computers. So quantum computer is something that uses the power of qubits as opposed to today's classical computers where we use logical bits that are either 0 or 1 at any point in time. Now, to really get the power of this, you've got to look at or think about what a qubit actually means, right? So if you take a classical bit today, 0 or 1, okay? Now, if you take a word of 4 bits, right? A 4-bit quantity can take any of 16 values from 0 to 15, right? So it can be any of those values, but any point in time, it can only take one value, obviously, right? That makes perfect sense. Now, things are a little bit different in the quantum world. since your qubits can be both 0 and 1 at the same time, if you take a 4-qubit word, all 4 qubits of that word are 0 and 1 at the same time. So that 4-qubit word represents 16 values at the same time. Very powerful concept. So instead of cycling through all the values of a traditional classical 4-bit word, you've got all of them at the same time. Now, the power of that becomes even more apparent when you start thinking about 8 bits, 16 bits, 32, and then start compounding the impact of that. So, how do you use this though? Some smart people have come up with quantum algorithms that exploit this behavior. And so the threat that we face today, right? I mean, on one side, it's very exciting that we'll have quantum computers. We'll be able to solve problems that we haven't been able to solve for a very long time. On the other, it brings a threat, right? The threat is that if we have a sufficiently powerful quantum computer, which we call a cryptographically relevant quantum computer, it's hard to say this, especially if you had a few drinks, but cryptographically relevant quantum computer. So I practiced it a few times, CRQC. Now, if one of those exists, it's got the potential to wreak havoc in the sense that it has the ability to break today's public key algorithms, right? Now, it doesn't exist yet. And what we see is that the day on which such a computer will be available is something we're calling Q-Day, right? So Q-Day is when we'll have a powerful enough quantum computer, they'll be able to break today's current asymmetric cryptography. Now, asymmetric cryptography is used in all these protocols like SSH and TLS and IPsec with digital signatures and so on. So it really impacts a lot of the encryption that we do on today's networks. So we don't have that computer today. The threat that we face right now is what we call harvest now, decrypt later, which is the fear that bad players out there could actually be recording conversations that they suspect have useful information that they can go and crack once a powerful enough quantum computer is available, right? So if you look at a TLS exchange, as I've shown there, you've got a few phases, right? So the first phase there is key exchange, where you can use an algorithm like Diffie-Hellman to basically, exchange a key that will be then used for encrypting the data that is being transmitted over that TLS session, right? So that asymmetric key exchange gives you a key that is then used for your symmetric encryption for the data. Now, if someone actually, bad players record that conversation, suspecting that it's got useful information, then, as I said, when a powerful enough quantum computer is available, they could go back, replay that conversation, be able to work out what the key is from the Diffie-Hellman exchange, and be able to decrypt the data, right? So that's one of the threats that we are considering right now. That if it does happen, then there's a potential that some data that we do not wish could get compromised. So how real is the threat? I don't want to sound the alarm here because we don't really know, right? We don't really know when we'll have a powerful enough quantum computer. This is about creating some awareness that it's on the horizon. So there are different opinions about when we'll have something powerful enough to be able to crack public key cryptography. And the measure that we're using here is having a quantum computer that can crack the RSA algorithm with 2048-bit keys in less than 24 hours, right? If you can do that, then it's something that we need to be worried about. Now, I've mentioned the idea of a sufficiently powerful quantum computer, right? And so, what makes a quantum computer powerful enough? It's really, there's a few dimensions there, but one of the key dimensions is the number of logical qubits it supports. So there's many sort of projections of how many qubits or the growth in the capability or the capacity of these quantum computers over time. And as you can see here, once again, the estimates vary in terms of when we'll have something like that available to us. So a lot of unknowns, a lot of things we do not know, right? But there is stuff we know. What we know is what is out there today. if you look at the table there, it's got a list of the top 10 most powerful quantum computers in existence in the world today. And the fourth column there indicates the number of qubits they have. And as you can see, they're actually pretty modest, right? It's not a lot of qubits. You're talking about hundreds of qubits. And that's not going to be enough to do anything really, impressive. But at the same time, there's a lot of development happening around quantum technologies. So, you've seen in the press in the last 12 months announcements from the likes of Microsoft, from Google, and so on, who are all coming out with quantum chips, right? A bit sketchy on detail, but they're still coming out with this, right? So you know that there's stuff happening in that space. Now, IBM expects that by 2033, we'll have quantum computers with thousands of logical qubits. Now, we don't really know how many qubits it's going to take in order to crack RSA, right, or Diffie-Hellman. There are estimates out there. We don't really know that. So once again, a few unknowns there. The one thing that we can be pretty sure about is that, if a bad player comes up with a sufficiently powerful quantum computer, they will not be out there telling everyone about it. They'll be exploiting it, right, gathering data, cracking it. So it may be out there today and we wouldn't know about it. That's how cryptography works, right? So we have to be prepared. So having said that, right, in what way does it really impact today's cryptography? I just want to go into a little bit more detail on that. So today, there's two primary ways of ensuring confidentiality of data exchanges that we have. One is by using symmetric encryption or symmetric cryptography, and the other one is using asymmetric cryptography. So I'll quickly go through that. Since you guys are in the security track, I'm sure you know all of this really, really well, so I will not spend too much time. But symmetric cryptography, very simple. You have a key that you come up with that has sufficient entropy, right? The key, well, the essential thing about that key is that it should be unpredictable. So if you have a long enough key with sufficient entropy, then you can be assured that you're pretty safe, right? Now, the same key is used for encryption and decryption. So Alice gets a bit of data, she encrypts it with a key, it goes to Bob, Bob decrypts it with the same key. So pretty straightforward, right? And this thing works really well. Now, the thing about symmetric cryptography is that when used in isolation, it doesn't really scale, right? Because you've got to have the same key at both ends. So, you need to somehow share the key between the communicating endpoints. So you're limited in terms of how far you can go with it. On the plus side, the algorithms that we have for symmetric encryption, like AES and Cha-Cha, and can be very efficiently implemented in hardware, right? So we have implementations today that can do it so quickly that the amount of latency introduced is actually very minimal. So it's really useful for encrypting bulk data, right? So it serves a great purpose there. The challenge is how do you get to the key to both the endpoints, right? That's always been the challenge with symmetric cryptography, because if you can intercept the key, then hey, it doesn't really matter how complex the algorithm is, how big the key is, your data will be suspect. So so how do we do it, right? One of the predominant ways of doing this is using pre-shared keys, a very manual process, a static process. You somehow generate a key with sufficient entropy, and you go in and configure it on both ends, right? As you can imagine, that doesn't scale, but we still use it, right? It's still used out there because it does give you that security. It doesn't scale. An alternative way of doing that is to use what we call quantum key distribution. So instead of manually going in and creating the key, what you do is you transmit the key material over a quantum channel. So what that gets you is it gets you a form of key distribution that is considered pretty well-nigh unbreakable, because you're using the properties of quantum mechanics, right? So when you're using QKD, you can be assured that if there is interception or eavesdropping of the key, you will detect it, right? And the attacker will not be able to get hold of that key. So it's a really interesting way of doing it. Now, those are like two ways of doing it, but the predominant way of doing this in a dynamic environment is to use an asymmetric protocol. So we use an asymmetric mechanism to actually exchange or share the key between the endpoints. So we create a channel that is secured by asymmetric cryptography to exchange the key that is then subsequently used for actually encrypting that bulk data using the symmetric key. So I'm getting a bit of a sort of hurry up there from Shamim, so I'll speed up. So the impact of quantum cryptography on symmetric keys or symmetric cryptography is not much, right? There is no efficient quantum algorithm that has a tangible effect on symmetric cryptography. So that means that we can continue to use whatever protocols we're using for symmetric cryptography, maybe increase the sizes of the keys to give us a little bit more protection, but it's inherently safe from quantum attacks, okay? Now, asymmetric key cryptography is where things get interesting, right? So we used the concept of a public key and a private key. You encrypted one, decrypt with the other one. And this is a great way of doing it because it does not suffer from the limitations that we have with symmetric cryptography. You can advertise the public key, it's out there in the open, keep the private key secure, and you're able to have your secure transactions between the two endpoints. And as I said, one of the applications of that is to exchange the key that is used with symmetric cryptography. So looking at asymmetric cryptography, right? The way we work out the private key and the public key is through mathematical algorithms. So we use this concept of a one-way function where we take in as inputs large prime numbers and use that to derive the public key and the private key, which is easy to do in that direction. But given the output of that, it's very hard to work out what the input was, right? Because we that mathematical problem of factorization is not really easily done using classical computers. So if you have a quantum computer though, then that problem becomes a lot easier to solve. And in fact, there's an algorithm that was developed by a guy called Peter Shaw that does precisely that. It speeds up factorization of very large numbers. And that means that pretty much all of the asymmetric algorithms that we are using today, if we have a powerful enough quantum computer, will be broken. So that has given rise to this whole movement around post-quantum cryptography, right? So post-quantum cryptography is coming up with new mathematics to replace the algorithms that we use in the public key world today, or public cryptography world today. So the post-quantum future, speeding up a little bit here, is for symmetric key, no real change. Continue doing what we're doing. We find as a safeguard, we could double the size of the keys, and that has negligible impact on today's computing capability, right? We should be able to safely do that without requiring to upgrade a lot of hardware out there. When it comes to asymmetric key solutions, we come up with new algorithms that we're calling post-quantum cryptography. So I'll quickly jump to that. The work that is being done to develop these post-quantum algorithms has been spearheaded by the NIST in the US. So they've come up with a number of algorithms, and they're actually part of the FIPS 203, 204, and 205 standard. One of them does key exchange in a way that is secure against classical computers as well as quantum computers, and the other two are used for digital signatures. Now, these algorithms are not sufficient by themselves. They have to be incorporated into the protocols. So there's been a lot of work going on in the IETF to then introduce them into the crypto suites that are part of protocols like TLS and IPsec and so on, right? So that work is happening quite rapidly. So going forward, that there is increasing awareness that this is a challenge out there, right? And the guidance for the industry out there is really do what we normally do in the security world, which is have a defense in depth strategy, right? So if you look at the different areas where these protocols play, these cryptography solutions play, symmetric key encryption, usually for bulk data. You do it at the network layer. So you could use that to secure all of the data flows that are going over your network. The public key cryptography typically uses the application layer. So where we're using today is, RSA, Diffie-Hellman, elliptic curve cryptography, replace it with post-quantum cryptography. Now, if you can do both of them, then you have an added layer of protection against quantum compute threats. Okay, I think that's an indication that I'm out of time here. All right, guys, thank you very much. I hope that's given you some idea.
Session 1. My name is Shane Hermoso from APNet.
Hello. Paresh, we don't have time for a question. Thank you. Can we have a big round of applause for Paresh Khatri? So,
I'd like to take this opportunity to
yeah, our next speaker is Shuki Liu. She came all the way from Beijing University, and she will be talking about inter-domain source validation based on AS relationship.
With that said, let's start. We will be.
Hello everyone. Today my talk is about our scheme of inter-domain source address validation based on AS relationships. I'm Shuqi Liu, and it's my work. I'm a student working for routing security, and it's my first time to attend APNIC. So I'm excited but nervous to present our work about inter-domain source address validation to you. And the presentation we talk about is mainly based on the draft about our draft about inter-domain source address validation based on AS relationships proposed in the IETF 7 networking group. And our scheme is mainly based on the RFC 5210. We have submitted several versions of our draft and shared our draft several times in the IETF working. Considering the actual internet and the actual world, the IP spoofing has caused many incidents and cause many security threats to the internet. And source address validation, which can be short for SAV, is an important way to relieve the IP spoofing and the DDoS attacks. So we take our basics. The RFC 5210 has divided the SAV into 3 levels, which is the exact network, intra-domain, and the inter-domain. And today, our talk is mainly about the inter-domain level, which is important, but now still lacks an effective and deployable standard. What's more, RFC 5210 also proposed an inter-domain source address validation based on the AS relationships, and the scheme and the idea is also the basics of our draft proposed here. Considering the background, our main motivation about proposing such a method is to design a deployable inter-domain SAV scheme to solve most IP spoofing cases. And so we choose to take the RFC 5210 as the basic to use the AS relationships. And we also try our best to implement our SAV system to design it with existing security mechanisms. Also, based on the comments and suggestions from IETF experts and researchers, we chose that our inter-domain SAV scheme adopts a distributed architecture. That is, it has no centralized server in each AS, and the scheme is deployed on all the existing routers. And the scheme takes no newly designed protocol and implemented with the BGP extension. And these 2 problems just you take the comments and the suggestions from experts and solve some problems may exist in the original standard, that is RFC 5210. And First, we come to the AS relationships. AS relationships, that is the basic knowledge of our scheme. That AS relationships are actually how ASs they engage, and they are usually realized as business agreements and finally translated into some constraints on traffic flows. So we chose to use AS relationships and combined with the IP prefix to estimate the inter-domain routes. In our draft and our scheme, we mainly talk about three major AS relationships. They are provider to customer relationship, peer-to-peer relationship, and the sibling-to-sibling relationship. And you can see the image, the table in the below. That is the export between the major AS relationships. And actually, the export rule, we think that they decide whether AS should have some roots. Besides all this about AS relationships, which have been discussed in the original RFC 5210, we also discuss about some complex AS relationships. The first is the hybrid relationship. It shows that they have different relationships at different interconnection points. And the second, is partial chancy relationships. It just restricts the scope of the typical P2C relationships. And knowing that what AS relationships are and there are some different types of AS relationships, another important thing is that we should know that the AS relationship can be obtained and then that can be utilized. So that there are many existing methods for us to acquire the AS relationships. The first is that direct announcement or agreement just between the neighbor ASs. They all deploy they choose to deploy the SAP, the inter-domain SAP together, so that they choose to direct announce or use the first agreement when they establish the session. And then is some inference algorithms. Many inference algorithms has been proposed since maybe 20 years ago, and some state-of-art methods such as ASRank, ProLink, and they are now used to infer the existing AS relationships. And also, there are some query methods like with RPKI, just like using the ASPA objects or the ASRA objects in RPKI, and they are objects that which are authorized to the provider or the AS relationship with the AS. But actually, the ASPA objects and the ASRA objects, they are all still in the drafts, and I think maybe there still will be need more between they become true standards and true like RFC. And then come to our design of our overall architecture of our design. And based on the original draft or original standard file, RFC 5210, and our design of our system, we temporarily named the interdomain SAP system AS relationship-based interdomain filtering, and we call it RBIF. From the image in the right, that we can see that we take it as mainly two key components. That is the first, the validation router VR, and the ASIP prefix mapping server. We call it AIMS. And to help with the later talking about our architecture and other things, we declare that the ASN or IP prefix SAP rules mentioned. That means the rules which show that whether the specific source ASs or specific source IP prefixes, they are valid. Firstly, we talk about the validation router. We call it VR. And in the RBIF system, we design it that to the existing border routers to take the role of validation router. And the validation routers, they establish ASN SAP rules through their advertisements and the updates to establish the ASN SAP rule. Besides this, the VRs also, they query the AIMS, the server regularly for the IP prefix corresponding to their needed ASNs to generate their IP prefix SAP rules, so that they get the IP prefix SAP rules and they verify the incoming packets with their IP prefix SAP rules to finish the source address validation. And based on the functions and the roles, we think the validation router should act as the implementation design. We take VRs to agree on the AS relationships using the BGP roles when establishing the BGP sessions. And besides this, considering the deployment and the deployment rate of different security mechanisms, we think that we should take the ASPA or ASRA objects in RPKI as a backup solution. Then come to the ASIP prefix mapping server, which is AIMS. And the function of the AIMS is very simple, that it should record the mapping from ASNs to IP prefixes owned by the ASs and offer it to VRs. Actually, all the authenticated information from the ASNs to the IP prefixes, they can be founded in the roles object in the RPKI, so that in the preliminary implementation design, we take RPKI as the trust anchor and the relying party to obtain the needed RPKI objects like the roles object. And what's more, based on this, the AIMS, they integrate the obtained role objects and generate the mapping from ASNs to IP prefix sets and provide it to the VRs. And we talk about this, and besides the RPKI, based on RPKI, maybe sometimes in some stable and simple networks without deployed RPKI, maybe sometimes a lightweight AIMS can be deployed first. And the lightweight AIMS, it can maintain the the mapping from ASNs to IP prefixes and of the neighbor ASs in the small network, and the information of other needed ASs, they can be obtained from the public services. And besides this, we talk as we use VRs, they work with the ASN SAP rule at the AS network, so that we think that the ASN SAP rule, they update less frequently than the BGP rules, so that we think that VRs, they can advertise the ASN SAP rules with the BGP update messages, so that a newly designed protocol is not needed, and we should try to implement it with the BGP update message extension, so that we primarily designed that use a newly designed BGP path attributes to transfer the ASN SAP rule updates, and its format is the typical TLV, and the value field carries ASN sets. And the example shows that how an update of the ASN SAP rules was transferred. Besides this, we conduct some simulation experiments, primarily simulation experiments in the GNS3 software. And when discussing and doing the experiment, we found that maybe there mainly have two key questions about the scheme and our design. And the talk and discussion of our SAP6 scheme mainly focus on the two key questions. The first key question is that how to obtain the neighboring AS relationships, and based on the methods we have talked about in previous slides, we mainly implemented it that use BGP roles to agree on the AS relationships when firstly establishing a BGP session, and then take the querying ASPR objects as a feasible alternative when under some situation that ASPR objects are more convenient. And in the simulation experiment, we just use a bird in the Ubuntu Dockers and in the GS3 Docker to act as the VR, and then it can receive and use the routinator as the relying party to get the needed RPK objects like rows, like maybe ASPAs from the from RPKI. And the second key question is that how to obtain IP prefixes corresponding to some ASs, and that's the key question about the data acquisition method of our scheme. And it's about that implementation of the AS IP prefix mapping server. So we in the RB system design, we mainly take the RPKI as the trust anchor and use relying party to get the needed objects in the RPKI, and in the design, the AMS, it integrates the row objects from the relying party and generates the mapping and offers to the VRs. In the simulation experiment, we just install the routinator as the relying party and use AMS functions to integrate the obtained row objects. And based on all the latest design and implementation and some discussion about our scheme and our draft, we think we have some next step for our further research. First is that we hope we should obtain more complex AS relationships and maybe more necessary connection scenarios from like engineers or like researchers to test our scheme and supplement it in more cases. And what's more, we should apply the current design into more situations, to more practical scenarios, so that we can combine with the results to get a better design and get more design, maybe for more situations. The third is that we should refine our implementations, enhance the security and maybe the efficiency and the overhead. And that's all of my talk today. Thank you very much.
Hello. Yeah. Yes. We can have one question. Anyone? Okay. So please give a big round of applause for Mr. Shukiliu. Ms. Shukiliu. Yep. Thank you. Our next speaker is Mr. Wilson Chow. He is the Managing Director for FutureGen International Private Limited, and he will be talking about AI-powered threat intel optimization. So can you have a big round of applause for Mr. Wilson?
Hello. Thank you, Shamin. So here we'd like to share our journey as to why we needed to reduce our IP blacklist that consisted of about 2 million into something smaller at around 50K at the time. Did this using AI. Forward this. A green button, sorry. So let me talk about the pain point, and a context. We see that in all over the world, cyber attacks have actually increased. You can see that in the blue line over there. And if we break the figure down by region, we see that our region actually, APAC, there in blue bar, is actually one of the highest recipients of cyber attacks. And so with that as the background, one of the traditional tools that we have as network defenders is to put in smart IP blocks at the edge of the network. So this is one of the traditional tools. However, that is not without disadvantages. So to us at the time, it opened up a gap in the market where we needed to offer some sort of protection, but also make it efficient. And so, taking off from a seminar that I attended with Mr. Barry Green over at Shadow Servers, I accessed their servers or their data and ask ourselves how many of the exposed routers in Asia Pacific and Japan included, Australia and were actually broken down by brand. And so in each of the countries, you will see that the majority of exposed firewalls in these countries are actually basic firewalls. So for each country, the top number one would either be MikroTik, or in some other countries, it's Fortinet. These two brands are basic firewall brands. Now, why is that of particular interest? We find that size really does matter for these instances because basic firewalls are not able to handle large IP block lists, right? But as we all know, the larger the list, the larger the covered protection. As you shrink the IP blacklist, you make it easier for lower level firewalls to operate them. But it's at the expense of giving better coverage. So here, our journey is we leverage AI to find that right balance where we are still able to block a majority of the attacks, but using a far, far smaller blacklist size. So here, we use AI for intelligent prioritization. AI can look at behavioral patterns and attack densities to figure out and rank by risk level the IPs that should be included in a smart blacklist. Next, using AI and ML, we are able to also use it for dynamic adaptation, where the algorithm adjusts itself depending on succeeding events that happen on a 7-day basis. Finally, because it's AI, we are able to command it to create smart lists that are adapted to particular firewalls. And what we found was that one of the key enabling factors of being able to reduce a 2 million blacklist IP into 50,000 was because of Pareto principle. So most of you will have known or heard about Pareto principle, where a small number of actors actually contribute to the majority of the events. So in our case, we show you a histogram. The leftmost side has the 0. It means these are the IPs that did not attack our network, followed by IPs that are seen between 1 to 10 times in a week. So these two alone are what we call the safely. These are the two categories that we can safely exclude from our smart blacklist. And they form the majority of the 2 million blacklists that will never be seen to be attacking your network. In contrast, on the rightmost side of the chart, we see a significantly slightly larger amount of IP addresses that are attacking in high volumes. And that's the one on your extreme right. So in a nutshell, this is our machine learning workflow for those of you that are data scientists among us. We do filter for false positives. We do smoke to take care of class imbalances before it comes up with a model. The model is then applied to the succeeding week's data, and we calculate the performance metric. Thankfully, this model came out, has a confusion matrix results with accuracy, precision, and F1 above 95%. When we actually deployed the smart blacklist, which is the smaller blacklist of 50K, as compared to the 2 million blacklist, you can see the dramatic drop in firewall CPU performance. Bulk 2 million blacklist, you can see that CPU at times rises to above 60-70%. In contrast, by using a 50K subset of that 2 million blacklist, the CPU resources remain consistently below 20%. In terms of effectiveness, the 50K was able to block 60-70% of all the attacks by volume. And in some weeks, we even see as high as 80-85% of the attacks being blocked. We also engage our friends in the industry. In particular, this is from J.R. Valdivia, who is a microtik guru in the Philippines. And we deployed the 50K smart blacklist to a microtik RB3011. And immediately it shocked them because the firewall started spitting out logs of violation. They never knew there was so much attacks on their network until they deployed that blacklist. And a snippet of the IP, like 2065.195.53, if you cross-check that with CrowdStrike, turns out to be a fairly aggressive attacker. Now, what is the effect on the microtik RB3011 when you load the 50K? So our concern was, because it's a basic firewall, it may not be able to handle 50K of IP blacklist. Turns out, the CPU did spike, but this one was during the ingestion of the scripts. Once it was ingested, there was 0% additional CPU load of running the 50K blacklist. Then we also use buffer bloat metrics to measure the impact of the 50K additional. Remember, these are basic firewalls that did not use smart list before. So the concern here for adoption was, if we do put in the 50K, how would it impact the user experience? And so the A+ grade says it all. Next, we also deployed that through the help of a friend who is the country manager for uas.com.ph, their distributors for Fortinet. And the same experience was shared with us. Immediately after putting the 5K, by the way, as a side note, Fortinet only accepts a maximum of 5K list. So we didn't even load the 50K, just the 5, but we loaded the top 5K list. And we estimated that it was still able to block anywhere from 50 to 60% of all the attacks by volume. And there are, again, the snippets of IPs that were blocked, which was cross-referenced to CrowdStrike and turns out to be malicious. Here, I'm almost done. we decided to open up this blacklist for the public. And as what Ms. Leslie was saying, security is a collaborative effort. This is just a start for us. The more people that help engage to make this list better, the better the performance. So those are the links to the MikroTik, Fortinet, and pfSense. And in summary, Smarter Blacklist without performance hit gives you improved firewall security and enables your IT security team to focus on the remaining 30%. And with that, I end my presentation. Thank you.
Okay. So, anyone has any question? No? This is nice. Thank you. Thank you. Can we have a big round of applause for Mr. Wilson again? This is the end of technical session 2, but not the end of day 1 of APNIC 60 conference. We have another 2 BOF. One is for IP abuse, meant to be here in this room, and another one is for next gen on the next room. And please don't forget, we have opening social in Ocean Ballroom here at this venue, starting from 7 p.m. So thank you again for joining technical session 2. See you really soon. Thank you.
You forgot to say the lightning talk was closed. Lightning talk.
Yeah, another announcement is we have closed the submission of lightning talk. So those who haven't submitted, please feel free to talk with me or Shane. And those who have submitted, if that is selected, please feel free to reach out again to know your talk time. Thank you.